A Brief History of Time by Stephen William Hawking. A sleepy summary. So let's drift into it slowly, the way the universe itself seems to drift, without hurry, without a clock ticking over it. Because for a long stretch of human history, nobody was even sure the universe had a beginning at all. Long before telescopes, long before anyone had done any of the mathematics, people simply looked up. They noticed that the sun rose and set, that the moon grew fat and thin and fat again, that certain bright wandering lights moved differently from the fixed, sleepy stars around them. A philosopher named Aristotle, watching the world with nothing but his eyes and his reasoning, decided the earth had to be a ball, not a flat plate, because he noticed that during an eclipse of the moon, the earth always cast a round shadow, no matter which way it was turned. A small, quiet clue, but a solid one, and it told him something true about the shape of the world he stood on. Aristotle believed the earth sat still at the center of everything, and that the sun, the moon, the planets, and the stars were all carried around it on invisible spinning spheres, layer upon layer, like the world was wrapped in something like glass onion skins, each one turning slowly around us. It felt right. It felt obvious, even. Why wouldn't the world we stand on be the middle of it all? Centuries later, a Greek astronomer named Ptolemy took this comforting, human-centered picture and worked it into a full and complicated model, complete with circles riding on circles, called epicycles, so that the strange backward loops that planets sometimes trace in the sky could still be explained without giving up the idea that the Earth was the unmoving center of everything. It was clever. It even worked, more or less, for predicting where the planets would appear. But it was also getting crowded and complicated, more like a machine held together with extra gears than a simple, elegant truth. Then, in the 16th century, a Polish astronomer named Nicolaus Copernicus suggested something quieter and stranger. What if the sun sat still instead, and the Earth was just one more planet, quietly circling around it like all the others? He didn't publish this idea until he was near the end of his life, worried, it said, about how the world might react to being told it wasn't the center of everything. And for a while, hardly anyone paid attention. It took nearly a century, and the work of a stubborn, sharp-eyed Italian named Galileo Galilei, before the idea began to take hold. Galileo pointed one of the very first telescopes at the sky and saw something that Ptolemy's old model could never explain. Tiny points of light circling the planet Jupiter, moons of their own, orbiting a body that was very clearly not the Earth. If the moons of Jupiter didn't need to go around us, maybe nothing did. Around the same time, a German astronomer named Johannes Kepler refined Copernicus's tidy circles into something even truer to what was actually observed. The planets, he found, don't move in perfect circles at all, but in gentle ovals, ellipses, sweeping faster when they are close to the sun and slower when they are far away. Little by little, the old snug picture of a still Earth wrapped in crystal spheres was coming undone, and something larger, colder, and far more spacious was taking its place. It was Isaac Newton, in the later part of the 17th century, who pulled this loosening picture together into something astonishingly solid. Newton proposed that every single object in the universe pulls on every other object, an invisible tug called gravity, and that the very same pull which drags an apple down from a branch is the pull that keeps the moon circling the earth and the earth circling the sun. One law everywhere for falling apples and wheeling planets alike. It was a beautiful unification, and it worked so well, predicting the paths of comets and the timing of tides and eclipses so precisely, that for the next 200 years or so, most scientists believed Newton's picture of the universe was more or less finished. Space was an enormous, unmoving stage, silent and empty, stretching out forever in every direction, and time was a river flowing steadily and identically for everyone, everywhere, ticking along at exactly the same rate whether you were standing still or racing through the void. It felt, once again, obvious. Space just is. Time just passes. What else could it possibly do? But before we drift further into how that snug picture also came undone, it's worth pausing here in this dim, comfortable dark to ask a small, sleepy question. What actually makes a scientific idea a good one? Hawking liked to say that a good theory has to do two things. It has to fit everything we've already observed, tucking in neatly around all the odd little facts we already know, the way a good blanket tucks in around your feet. And it has to make predictions clear enough that they could, in principle, turn out to be wrong, because a theory that can never be wrong can never really be tested at all. It can only ever be shown, again and again, not yet false, never fully proven, only trusted a little more each time it survives another test. That's really all any of our grandest ideas about the universe can ever be. Not a final, sealed truth, but the best guess we haven't managed to break yet. Keep that thought folded gently somewhere in the back of your mind as we go on, because almost everything we are about to wander through together, the Big Bang, black holes, the strange dance of tiny particles, has that same soft, provisional shape. Our best guess, held loosely, ready to be revised the moment the universe whispers something new. Now back to Newton's calm, silent stage of space and time, because a young patent clerk in Switzerland was about to gently pull the whole floor out from underneath it, and yet somehow make the universe feel even more orderly once he was done. His name, of course, was Albert Einstein, and in 1905 he noticed something odd about light. No matter how fast you are moving when you measure it, light always seems to travel at exactly the same speed, about 186,000 miles every single second. It doesn't matter if you're standing still or running toward the light source or racing away from it as fast as a rocket can carry you. The speed of light you measure never changes. This sounds like a small technical detail, the kind of thing that might make you yawn and roll over, except that it breaks something we normally take completely for granted. The idea that speeds simply add together. If you throw a ball forward from a moving train, the ball's speed relative to the ground is the train's speed plus the throw's speed. Simple. But light doesn't behave that way. However fast you chase it, it always slips ahead of you at the very same steady speed. And if that's true, Einstein realized, then something else has to give. If speed is distance divided by time, and the speed of light insists on staying constant no matter how you're moving, then distance and time themselves must be able to stretch and shrink to keep that speed constant. This is the heart of his special theory of relativity. There is no single universal clock ticking the same for everyone in the universe. Time runs differently depending on how fast you're moving. A person on a very fast rocket ship, from the point of view of someone standing still and watching, would seem to age more slowly. Their clocks would tick behind. This isn't a trick of instruments or perception. It is, as strange as it feels while your eyelids are drooping, simply how time behaves. And space and time, Einstein showed, aren't really two separate things at all, but woven together into a single fabric physicists call space-time, 4 dimensions instead of 3, with time itself as intimately bendable as up, down, and sideways. 10 years later, in 1915, Einstein finished an even grander version of this idea, called general relativity, and this is where gravity itself gets a beautiful, dreamy new explanation. Newton had imagined gravity as an invisible pulling force reaching out across empty space, one object tugging on another the way an unseen hand might tug a string. Einstein imagined something gentler and stranger. He said that mass, the stuff that makes up stars and planets, and yes, even your own sleepy, heavy body, actually bends the fabric of space-time around it, the way a heavy sleeping cat resting in the middle of a soft, stretched blanket will make the blanket dip and curve. Other objects moving nearby aren't being pulled by any invisible hand at all. They are simply following the straightest possible path they can, through a space-time that has been curved and dented by whatever heavy things are sitting in it. The Earth doesn't orbit the Sun because the Sun reaches out and grabs it. The Earth orbits the Sun because the Sun's enormous mass has curved the space-time around itself into a kind of gentle valley, and the Earth is simply rolling along the bottom of that valley, forever falling, forever missing, tracing out the path we call an orbit. Gravity, in other words, is geometry. It is the shape of space and time themselves, bent by whatever heavy things happen to be resting inside them. And because light itself travels through this same curved space-time, even something as weightless and quick as a beam of starlight will bend slightly as it passes close to something massive, like our own sun. When astronomers finally measured this bending during a solar eclipse in 1919, watching starlight curve exactly the amount Einstein had predicted, it was one of the great confirming moments of modern physics, the whole world blinking awake to the fact that space and time were far stranger and softer than Newton's old rigid stage had ever suggested. Let your mind settle here for a moment on just how strange this really is, because it will matter again later, when we drift toward black holes. If space and time can be curved and stretched by mass, then near something extremely massive, time itself moves more slowly and space becomes more tightly warped. Push that idea far enough, pile up enough mass in a small enough space, and you can imagine the curving becoming so extreme that it stops being a gentle dip in the fabric and becomes something closer to a bottomless well, a place from which nothing, not even light, both the fastest and lightest thing there is, could ever climb back out. Keep that picture folded away too. We'll return to it. But first, let's drift outward further than any planet, past the edge of familiar starlight, out to where the universe as a whole was beginning to reveal one of its biggest secrets. In the 1920s, an American astronomer named Edwin Hubble was using one of the largest telescopes in the world at the time, up on a mountain in California, to study faint smudges of light that other astronomers had assumed were simply clouds of gas somewhere within our own galaxy. Hubble discovered that many of these smudges were not clouds at all, but entire other galaxies unimaginably far away, each one containing billions of stars of its own, our own Milky Way suddenly just one galaxy among countless others scattered through the dark. That alone was enough to make the universe feel enormously larger and lonelier than anyone had guessed. But Hubble noticed something even stranger as he kept watching. The light coming from these distant galaxies was shifted toward the red end of the spectrum, and the further away a galaxy was, the more its light was shifted, and the faster it appeared to be receding from us. This is called redshift, and it works something like the sound of a passing ambulance. As a sound source moves away from you, the sound waves stretch out and the pitch drops lower. As a light source moves away, the light waves stretch out too, shifting toward the red. What Hubble had found, in other words, was that almost every galaxy in every direction was rushing away from every other galaxy, and the further apart two galaxies were, the faster they were flying apart. The universe, it turned out, was not the still, unchanging stage that Newton had imagined, and that even Einstein, at first, had wanted to believe in. Einstein had actually added a fudge factor to his own equations, a cosmological constant, specifically to keep the universe standing still, because the idea of an expanding universe felt too wild even to him at first. He later called this one of the biggest blunders of his life, because the universe, it turns out, really is expanding, every galaxy drifting apart from every other galaxy, the whole vast fabric of space itself stretching outward like the surface of a balloon being slowly inflated, carrying the little dots painted on its surface further and further apart from each other, even though none of the dots are moving across the balloon's surface on their own. And here is where the sleepy, dreamlike logic of an expanding universe leads somewhere enormous. If everything is moving apart from everything else right now, then if you let time run backward in your mind, like rewinding a film, everything must once have been closer together. Rewind further and closer still. Rewind far enough, all the way back, and you arrive at a moment when the entire universe, everything, all the galaxies, all the stars, all the space between them, must have been squeezed down into an unimaginably small, unimaginably dense point. This is the Big Bang, not an explosion happening at some particular place inside an already existing space, but the beginning of space and time themselves, everything expanding outward from that first tiny, searing moment roughly 13 or 14 billion years ago. It's a strange thing to try to picture, because our minds want to ask what was there before it and where it happened. But if time itself began at that moment, then asking what happened before the Big Bang may be a bit like asking what lies north of the North Pole. There simply isn't a before, because time, the very thing that lets us have a before and an after, hadn't started yet. Hawking spent a great deal of his working life circling this exact puzzle, wondering whether the universe truly had a single, sharp starting instant, a singularity, where all our equations simply break down and stop making sense, or whether, once you looked closely enough with the right combination of gravity and quantum theory, that sharp beginning might soften into something gentler, a universe with no true edge at all, the way the surface of the Earth has no edge you can fall off of. Even though it's still perfectly finite, to understand why that softening might even be possible, we have to leave the enormous and drift down, down, down into the unbelievably small, because it turns out the smallest things in the universe behave in ways just as strange and dreamlike as the largest ones. In the early 20th century, physicists working out how atoms and light behaved kept running into the same puzzling wall. Tiny particles simply refused to behave the way solid, sensible objects are supposed to behave. A German physicist named Werner Heisenberg discovered something that came to be called the uncertainty principle, and it says, roughly, that you cannot ever know both the exact position and the exact speed of a tiny particle at the same time. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving, and the other way around. This isn't because our instruments are too clumsy or not yet good enough. It's not a limit on our measuring tools at all. It's a limit woven into the fabric of reality itself, a fundamental fuzziness that exists whether or not anyone is even trying to measure anything. Down at that scale, particles don't have one single definite position and one single definite speed just waiting to be discovered. They exist instead as a kind of shifting cloud of possibilities, more like a smear of probability than a hard little dot. This strange, fuzzy behavior is the foundation of quantum mechanics, and it means that empty space itself, even a space with nothing at all in it that we would normally call something, is never quite perfectly empty. Because of the uncertainty principle, tiny pairs of particles are constantly, briefly popping into existence out of nothing at all. A particle and its opposite twin, an antiparticle flickering into being for the barest sliver of an instant before rushing back together and annihilating each other, vanishing again as if they'd never been there. Physicists call these virtual particles, and this restless, fizzing quantum foam turns out to matter enormously later when we drift toward the edges of black holes. Let's take a moment here, in the middle of all this cosmic strangeness, to simply notice how different the world of the very small is from the world of chairs and cups and pillows that we are used to. Down among atoms and their pieces, protons and neutrons and electrons, and further down still among the quarks that make up protons and neutrons, and the various other tiny particles that carry the fundamental forces of nature, ordinary common sense, simply stops applying. There are four basic forces that physicists have identified as governing everything that happens in the universe. There's gravity, the weakest of the four by far, yet the one that shapes galaxies and holds planets in their orbits, because it works over enormous distances and always pulls, never pushes. There's electromagnetism, the force behind light, electricity, magnets, and the chemical bonds that hold molecules and you together. There's the strong nuclear force, which glues quarks together inside protons and neutrons, and holds the nucleus of an atom together despite how fiercely the positively charged protons inside it want to repel one another. And there's the weak nuclear force, responsible for certain kinds of radioactive decay, quieter and stranger than the other three, but essential to how stars like our Sun manage to shine at all, fusing hydrogen into helium and releasing the warm light that right now, however many miles and years away, once fell on the leaves outside whatever window you fell asleep near as a child. One of the great, unfinished dreams of physics, one that occupied a great deal of Hawking's own thinking, is whether these four forces, so different in strength and behavior, might actually be four faces of one single, deeper force, a unification that would have looked seamless in the impossibly hot, impossibly dense conditions of the universe's earliest moments, and that only split apart into four separate-seeming forces as the universe cooled and stretched. Physicists call the search for this deeper unity the search for a grand unified theory, or when gravity is folded in two, a theory of everything, one elegant set of equations that could, in principle, describe absolutely everything that happens anywhere at any scale, from the smallest flicker of a virtual particle to the largest sweep of galaxies drifting apart across the sky. Now gently, let's go back to that idea we folded away earlier, the well in space-time, because it's time to talk about black holes, and there is something wonderfully calming in its own eerie way about how simply and inevitably they arise from everything we've already wandered through. Stars, for most of their long lives, exist in a kind of balance. Deep in their cores, nuclear fusion is constantly happening, hydrogen crushing together into helium, releasing enormous amounts of energy and light, and this outward pressure of light and heat pushes back against the star's own gravity, which is always trying to crush the star inward under its own weight. For billions of years, a star like our Sun burns steadily, outward pressure and inward gravity locked in a long, patient standoff. But eventually, a star runs out of fuel to burn, and once the outward pressure of fusion fades, gravity, which never stopped pulling, finally gets to win. For an ordinary star like our Sun, this ending is fairly gentle. It swells up, sheds its outer layers, and settles down into a small, dense, slowly cooling ember called a white dwarf. But for a star much more massive than our Sun, gravity's final victory is far more dramatic. The star's core collapses in on itself with such tremendous force that it can crush right past the point where any known force can push back, past the point where even the star's own particles, jammed together as tightly as physics allows, can resist any further. The core keeps collapsing and collapsing and collapsing, all of that mass folding down into a point of space so small and so dense that the surrounding space-time curves in on itself completely, forming what astronomers call an event horizon, an invisible boundary in space beyond which the pull of gravity is so absolute that nothing, not light, not radio waves, not any signal or object of any kind, can ever climb back out once it crosses inside. This is a black hole, not a hole in the ordinary sense, not an empty gap, but a region of space-time curved so extremely that it has essentially sealed itself off from the rest of the universe, a one-way door that only ever opens inward. It's worth sitting with how strange and quiet this idea really is. From outside, a black hole isn't glowing, isn't screaming, isn't doing anything dramatic at all. It simply sits there, a patch of utterly ordinary-looking darkness, betraying its presence only by the way it bends the light of anything passing near it, and by the way it swings nearby stars and gas into fast, tight orbits around something that otherwise cannot be seen. If you imagine falling toward one, and please just imagine it gently, the way you might imagine floating in a pool rather than actually drowning in it, an astronaut falling toward a black hole would notice something odd. From their own point of view, nothing dramatic seems to happen as they cross the event horizon. There's no wall, no barrier, no signpost. They simply keep falling. But someone watching from a safe distance would see something entirely different. Because time itself runs more slowly the deeper you go into a strong gravitational field, the falling astronaut would appear, to the outside observer, to move more and more slowly as they approached the horizon, their image growing dimmer and redder and slower, seeming almost to freeze there forever, never quite visibly crossing over, even though from the astronaut's own perspective, they crossed over in an ordinary instant and continued falling toward whatever waits at the center. And this is where Hawking made one of his most important and most surprising contributions, because for a long time, physicists assumed that black holes, once formed, were the most permanent things in the universe, prisons with no possible exit, growing only ever bigger as they swallowed more matter, never smaller. But remember that restless, fizzing quantum foam we talked about earlier, all those pairs of virtual particles constantly popping into existence out of nothing, right at the very edge of what we'd normally call empty space. Hawking realized that right at the boundary of a black hole's event horizon, something remarkable could happen to those flickering virtual pairs. Sometimes one particle of a pair might happen to form just inside the event horizon, doomed to fall forever into the black hole, while its partner happens to form just outside, free to escape. Normally, these pairs would simply meet back up and vanish, cancelling each other out as though nothing had happened. But if the horizon separates them before they can reunite, the particle outside doesn't have anything left to annihilate with, and so it becomes real, escaping outward as actual radiation, while the particle that fell in effectively subtracts a tiny sliver of mass from the black hole itself. This faint outward trickle of radiation is now called Hawking radiation, and it means that black holes are not perfectly permanent after all. Ever so slowly, over spans of time so long they make even the age of the universe look brief, black holes lake away their mass and energy, shrinking, and eventually, in the almost unimaginably distant future, evaporating entirely. It was a beautiful and unexpected bridge between two of physics' biggest ideas, quantum mechanics down in the tiny fuzzy world of particles, and general relativity out in the enormous curved world of gravity and spacetime, meeting each other right at the black hole's edge. And it remains one of the clearest hints we have that these two great theories, which still don't fit together perfectly everywhere else, must ultimately be talking about the very same underlying universe. Let your thoughts rest on that a moment. Even something as seemingly final and absolute as a black hole is, in its own extremely patient way, letting go, breathing out, ever so slowly returning its borrowed mass back to the universe it came from. There is something almost comforting in that, in the middle of all this vastness, nothing, it turns out, not even the darkest, heaviest thing physics knows about, is entirely without an exit, even if that exit takes longer than stars themselves have existed. Now drifting sideways for a moment into a question that might seem almost too ordinary to belong here among galaxies and black holes. Why does time only ever seem to move in one direction? Why do we remember the past and not the future? Why does an egg, once broken, never spontaneously unbreak itself back into a whole egg sitting neatly on the counter? Hawking spent some time in his book gently unpacking this, because it turns out there isn't just one arrow of time, but several, all pointing quietly the same way. There's the thermodynamic arrow of time, which has to do with a property called entropy, a rough measure of how disordered or spread out a system is. In an ordered room, there are relatively few ways for things to be arranged and still look tidy, but in a messy room, there are enormous numbers of possible messy arrangements. So as things are left to themselves, they tend to drift from order toward disorder, simply because disorder is so much more statistically likely, so much roomier, so much easier to fall into than any one particular tidy arrangement. This is why an egg can break into a disordered splatter far more easily than a splatter can reassemble itself into an egg. There are countless disordered configurations and only one very specific ordered one. So time, left to its own devices, tends to slide from order into disorder. And this steady increase of disorder is one of the ways we can tell that time is moving forward at all. Then there's the psychological arrow of time, simply the fact that our minds remember the past and not the future, which Hawking suggested is deeply tied to this same increase in disorder, because our brains, in the very act of forming a memory, are themselves small orderly systems increasing the disorder of the world around them as they use up energy. So remembering always happens in the same direction that disorder increases. And finally, there's the cosmological arrow of time, the simple fact that the universe is expanding rather than contracting, which happens to point in the very same direction as the other two. Hawking wondered, in his more playful and speculative moments, what might happen if the universe someday stopped expanding and began to contract instead. Would time itself somehow run backward, eggs unbreaking, memories flowing from future into past? He eventually leaned away from that particular idea, but the question itself is a lovely, dizzying thing to drift off thinking about. That the direction time seems to flow may not be some ancient cosmic law at all, but simply a quiet consequence of the universe having begun in a very orderly state and slowly, gently, spreading out into disorder ever since. The way a held breath eventually has to be let out. And speaking of playful, speculative moments, Hawking also spent some time wondering about wormholes, hypothetical shortcuts through the curved fabric of space-time, tunnels that might, in principle, connect two very distant points in space, or even two different points in time, allowing something to travel between them far faster or far earlier than the ordinary straight route would allow. He treated the idea of time travel with a kind of amused, careful skepticism, noting that if travel into the past were ever truly possible, you'd expect the universe to be at least a little cluttered with tourists from the future. And since we don't seem to be visited by any, he leaned towards suspecting that the laws of physics quietly conspire to prevent it. Some deeper principle, not yet fully understood, that keeps history from being allowed to contradict itself. It's the kind of idea that isn't meant to be answered so much as gently turned over in your hands before you set it back down and let your mind wander on. By this point in your drifting, drowsy tour of the universe, a pattern might be forming, the same one that quietly ran underneath everything Hawking wrote. That our two greatest theories of physics, general relativity for the huge and heavy, quantum mechanics for the tiny and fuzzy, work extraordinarily well within their own separate domains, and yet don't quite agree with each other where they overlap, especially in the strangest, most extreme places, like the very center of a black hole or the very first instant of the Big Bang, where enormous mass is compressed into an infinitesimally small space, and both theories are needed at once, and both, when combined, tend to break down into nonsense, spitting out infinities where there should be sensible numbers. Solving this puzzle, weaving gravity and quantum mechanics into one single, seamless theory, is what physicists mean when they talk about a theory of everything. And it was the great unfinished dream that Hawking circled for his entire working life. Various candidate ideas have been proposed over the years, string theory among the most famous, which suggests that the truly fundamental building blocks of the universe aren't point-like particles at all, but unbelievably tiny vibrating strings of energy, far too small for any instrument we currently have to ever directly see, with different vibration patterns giving rise to all the different particles and forces we observe. The way different notes can come from a single vibrating guitar string, whether string theory or some other idea entirely turns out to be the right path toward unification, is still an open question, one that remains, even now gently unresolved, a puzzle still waiting on a bedside table somewhere for physicists patient enough to keep working on it. Toward the end of his book, Hawking allowed himself to drift into something closer to wonder than equation, closer to a hush than a lecture. He pointed out that if we ever did discover a true, complete theory of everything, one elegant set of equations capable of describing absolutely everything the universe does, it would be, in a sense, the ultimate triumph of human reason, not just a description of how the universe behaves, but potentially an explanation of why the universe exists at all, why there is a universe for these particular laws to describe, rather than simply nothing. He wondered, with the kind of gentle humor that runs through much of his writing, whether finding such a theory would mean we finally understood the mind of the universe itself, why it bothers to exist, why we, tiny thinking creatures made of stardust and curiosity, happen to be here to ask about it in the first place. It's a question that doesn't really have a tidy answer, and Hawking, characteristically, didn't pretend to hand us one. He simply laid the question down at the very end of a long, careful walk through everything else, the same way you might lay down a book on a nightstand after the last page, the light already dim, the question still glowing faintly in the dark long after you've closed your eyes. So here we are, at the end of this long, slow drift, having wandered from an Earth once believed to be the unmoving center of everything, out through Copernicus's quiet rearrangement of the sky, through Galileo's telescope and Newton's falling apple, into Einstein's bending, breathing fabric of space and time, out to Hubble's discovery that the universe itself is stretching, expanding, carrying galaxies apart from each other like dots on the surface of a softly inflating balloon. Backward in our minds all the way to the searing, unimaginable density of the Big Bang, down into the fuzzy, uncertain world of quantum particles flickering in and out of existence in what looks like empty space, out again to the enormous crushing gravity of collapsing stars folding themselves into black holes, and the strange, patient leak of Hawking radiation letting even those darkest places slowly let go of what they've swallowed. Sideways into the quiet mystery of why time only ever seems to walk forward and never back, briefly into the playful, unresolved question of wormholes and time travel, and finally up to the very edge of what physics can currently reach, the still unanswered dream of a single theory that could hold everything, the large and the small, the heavy and the fuzzy, gravity and quantum mechanics, all in one gentle, unified account of why anything is the way it is at all. None of it needs to be memorized. None of it needs to be solved before you fall asleep, and none of it will be, not tonight, and possibly not for a very long time yet, because these are some of the deepest, oldest questions our species has ever asked, and even the brightest minds working on them are still, in their own way, just gently feeling around in the dark for an answer they can trust. What Hawking seemed to want, in writing all of this down so patiently, was simply for more people to feel allowed into the conversation, to feel that the universe, however vast and strange, is not something reserved only for physicists in lecture halls, but something that belongs, a little bit, to everyone who has ever looked up at a clear night sky and felt small and curious at the same time. So let the galaxies keep drifting apart out there, unhurried, at their own patient pace. Let the black holes keep leaking their slow, quiet radiation into the dark, one imperceptible sliver of mass at a time. Let the tiny particles keep flickering in and out of a universe that was never really empty to begin with. None of it is waiting on you. It was all unfolding long before you closed your eyes tonight, and it will still be gently unfolding at exactly the same unhurried pace, however long you sleep, and it will still be there, quietly turning, humming with its own slow physics, whenever you happen to open your eyes again. And in the end, this sleepy summary, with its relaxing tone and warm glow, is not meant to replace something. It is meant to honor and point toward a much larger light. It is offered with care and with the genuine hope that something in tonight's listening finds its way into you as an invitation. The whole book is waiting. The real depth lives there, in every word they chose and every story they told and every quiet idea they let breathe across a full page. Let this be the beginning of something you carry forward in the light of an ordinary tomorrow, and if this lamp has helped you in some way, a light keeps it burning for someone else who might need it too.